The backflow algorithm is a fairly quick and methodical process for finding the critical path in a project diagram. And in so using the backflow algorithm, you'll also be finding the critical times for not just the whole project, but every individual vertex in the whole graph, which is something very useful as we discussed in the last video. But the main purpose of this video is to try to teach you how to simply use that backflow algorithm, and also so we can understand how it's working, because it's a little bit weird. And if you read the algorithm as it's presented in the textbook, it's very wordy and it can be a little bit difficult to understand if you're not a math person. It just the lingo is a little bit hard to follow in my opinion. I mean, I understand it, but a lot of students have had a little bit of trouble with this. So we'll do an example of using it to generate a priority list. But let's go ahead and read through the algorithm. Step one, it says to find the critical time for every vertex in the diagram. So that's the main goal of what this algorithm is going to do. And it says this is done by starting at the end and working backwards towards the start. And this is why it has its name, backflow. We're going to work our way backwards through the whole graph. And as I said in the last video, it's easier to start at the end, because the end, the critical times are way easier to find. And when you work your way backwards, it's easier to solve them if you work your way back from the end back forwards. And it says this is done by according to the following rule. The critical time for a task X equals the processing time of X plus the largest critical time among the vertices incident from X. So that's quite a sentence. Let me grab my laser pointer so that I can point at it. But basically, let's say I was trying to find the critical time of this vertex. What it says to do is I want to take the critical time of the look at all the critical times of the vertices incident from it, and that all that means is ones that are stemming directly from it, come after it, basically have an arrow attached to it, to a target from it. And it says that the critical time for task X is equal to the processing time of X. So like if I was throwing numbers here, basically X would, let's say this was task A and this had a processing time 5. We're going to take that and add whatever the largest critical time that comes from it. So let's say that these each have their own critical times, 2, 5, 7. We're going to add the largest one. So let's say this one's the 7. 7 plus 5 is 12. And I promise when we do an example, this will be easier to follow, because it's very abstract as we're looking at it here. It says the general idea is illustrated in figure 8.19. But basically, if we start over here, if we know the critical times over here, we just use the simple rule to find the previous ones. Then once we know this one, we could use the same rule to find the next one, and we're going to start at the end and work our way back by doing so. And also, this is quite important. It says to help with the record keeping, it is suggested that you write the critical time of the vertex in square brackets to distinguish it from the processing time in parentheses. So when we have our digraphs, we are given the processing times using parentheses like 5 minutes or 5 hours or whatever, but these numbers are going to mean something different. And we're just going to use brackets to make sure that we are not getting confused about what the numbers mean. The brackets will always indicate critical time as opposed to processing time, where processing time is how long the task takes to finish, and critical time is how long total from here at minimum it will take to finish the project. And then once you do that, the critical path algorithm is just done by using the backflow algorithm, creating a priority list, and then everything is the same from there. So let's practice applying the backflow algorithm in the exact same IKEA example we were just working on. So in this case, let's try to find all the critical times of this project, and we're going to put them all in brackets instead, because I already have all the processing times in parentheses, which is something you won't always need to be given. But just as a reminder, we're going to start at the end and work our way back. So the end is as I said before, this is not really a necessary point, because there's no time associated with finishing the project. So this one I would generally just skip. But you could say that this has a critical time of 0 if you want, but I wouldn't even bother. But if I'm going backwards from the end, what I would then want to look at is, well, what are the critical times of each of these points? And these are the easiest points on the whole graph because they only have one path to the end, right? Once I finish those, the project is done. So with FW's critical time is going to be 6, because the numbers that come from it, if I was to put a bracket there, would be 0, and 6 plus 0 is 6. We're always going to add the target, basically. We're going to be adding our way backwards. PD's critical time is only going to be 3 because once we finish it, it's done. That's it. That's so what you could remember is the critical time for the vertices at the very end are always just equal to their processing times because there is nothing to add to them. The project is just going to be finished in that specific path. Of course, we have to do them all, but we're not taking that into account. We're just taking into account all the paths from that point to the end, to which there is only one. And now, once we have those, we could work our way backwards. Next, we could do IC. So for IC, there's only one path from IC to the end, but the critical time will be the sum of all the points. And if we're focused on exactly that rule, we're going to take the processing time of IC and add that to the critical time of the vertex from it. So IC is going to be 1 plus 6, which is 7, of course, because it's the sum of all the times in the project. And now, if I'm working my way back to HU is a little harder, even though we already figured it out, because we did that in the last video, finding the critical time of HU, which was 11. Notice now we have 3 targets, and this is where you need to be a little bit more careful, because the rule is you're going to take the processing time of that vertex and add the largest bracketed number to it. So by rule, it's going to be 4 plus 7, which is 11. And that would give us the critical time of HU, which is consistent to what we got before. But this is what I wanted to explain, is that as you're working your way back, you need to have all of the vertices that are incident from it, just meaning the ones that are after it. And we're going to take the biggest one and add it to the processing time. And also that makes sense because if we're looking at all these paths, we want to follow the biggest one, because if I'm thinking about all these paths, the critical path is going to be the longest. And obviously this one, this path is longer than any of these, which is why we choose this one for a critical path. And then if we added up 4 plus 1 plus 6, well, this number indicates already the sum of those numbers. So if I add this one to it, this would be the sum of all of them. So it's like we're adding our way up backwards and always choosing the largest because that would find the critical path from there. Now to finish, we're just going to keep doing that. So working next on PU, it does kind of matter because I don't want to go to IP now because I can't solve IP until I know its bracket. You always need to find the bracket before. So you don't want to just do 11 plus 4 to get 15, though that's technically correct, because I want to make sure to know, well, what's the critical time of this one, because I need to figure out which one of these is larger. But if I go from PU only has one target, so in some cases it's very easy because there's no choice. HU was a little more complicated because I had 3 choices, and I needed to pick the larger of them all. But with PU, I only have one choice, which is EU. EU's critical time is 2, so 2 plus 3 is 5. That would give me the critical time of PU. And now if I'm going back to IP, again, we have 2 choices. I need to make sure to have both of them solved first. And what I can see is that HU has a larger critical time, so I'm going to add that. 11 plus 4 would be 15, which would give me IP. But basically, it's just a matter of adding. And as long as you know what you're adding, that's the key. And you're always adding the brackets that come right before it. And making sure to only use the largest one. You're not adding them all together, just picking the largest. So for PL only has one target, IC. IC has a critical time of 7. So 7 plus 4 is 11. And that's kind of how I work my way back. I'm always looking at, well, what's coming from this? What are my choices before I move on? And I like to scan my way from left to right. So I would do ID next, then IW, then IF. Because we're working our way backwards, it's a lot harder to do this from left to right. From right to left, it's a lot easier to find via Backflow. For some reason, my brackets all moved there. I don't know what happened. But ID, since PU's critical time is 5, 5 plus 5 is 10. I only have one choice, so that's easy. With IW, I have 2 choices. IP is 15, ID is 10. Choose larger. 15 plus 7 is 12. Sorry, 22, of course. Then IF, 22 is larger than 11, so 22 plus 5 is 27. Now, moving my way back to the first line, or the first set of ready tasks. AP 7 only has one target, 27. 7 plus 7 is 34. AF has one target, 27. 5 plus 27 is 32. AW, one target, 22. 22 plus 6 is 28. And then 8 has one target, 10. 8 plus 10 is 18. And once we have them all, we are now done with the backflow algorithm. We have solved the critical times of all the vertices in the project. Actually, sorry, I skipped step 2. We're not done. We're done with step 1. Step 2 says once we have the critical time for every vertex in the project as we do now, critical paths are found by just following the path along the largest critical times. In other words, the critical path for any vertex x is obtained by starting at x and moving to the adjacent vertex with the largest critical time. So basically what it's saying is choose the biggest number and keep choosing the biggest number in every case. So from the start, we would go to AP first, because that has the largest critical time of all. And also notice that the largest number you get is going to be critical time for the whole project, because that represents the longest chain of events progressing all the way forward through the rest of the project. But if I follow along that path, that has to go to IF. From IF, I'm going to choose the larger number, which would be IW was bigger than PL. Then IP was bigger than ID. HU was bigger than PU. Or sorry, yeah. Then IC was bigger than all the rest, and so on. But that is exactly the same path we had before. And basically, it will help us figure out which path took the longest by tracing along all the largest numbers. And while that was quite a long example, once you get the hang of this actually goes pretty quick. But my goal in this video was to hopefully make it understandable. Why are we doing this? But working your way backwards is a much easier way of determining the time of completion, because the ones at the very end were super easy because the project's almost done. And then I kind of am using them in succession to figure out, okay, well then what would be the shortest from here? Then from here, then from here. And next up, to actually solve, now we can use these numbers to build a good priority list. And that's exactly what the critical path algorithm is all about, something we will see in the next video.